Okay, so now we're ready to use our main result, which was again that if the limit of the function approaches a value, then the sequence also approaches the same value. So here we have the sequence defined by the formula, n cubed over n to the fourth plus 16. And we want to look and see if this converges. So the way that we do this, check convergence, is by taking the limit of the underlying function. So we do the limit as x goes to infinity of x to the third over x to the fourth plus 16. We could use L'Hopital's rule here to deal with this because this is an infinity over infinity. But because that's an x to the third and that's an x to the fourth, it's going to take several applications of L'Hopital's. Instead, we realize that in this fraction, the only thing that matters in the top is the largest power present. The only thing that's going to matter in the bottom is the largest power present. So I can say that this thing is the same as this limit. And that thing, x cubed over x to the fourth, I can simplify to be 1 over x. And now I know if x goes to infinity, 1 over x goes to 0. So therefore the underlying function goes to 0. And therefore the sequence then converges to 0. Right? Since the underlying function goes to 0, then the sequence will also converge to 0. So we were able to work that out, again, using that idea that in a polynomial, the only thing that matters is the largest power. We did that for both top and bottom. Gives us something we can simplify, and we can do an easy limit with. Let's look at a second example here. So very often we will describe sequences by their formula, as we're doing here. So here we have k over square root of 9 k squared plus 1. Okay? So we begin by looking at the underlying sequence, so we convert it over to x. So this would be x over the quantity 9x squared plus 1 to the 1/2. Okay, so this, of course, is an infinity over infinity, right, limit. So we attempt L'Hopital's rule. We attempt to use L'Hopital's rule. So we take the derivative, limit as x goes to infinity. Derivative of the top is 1 over the derivative of the bottom. What's the derivative of the bottom going to be? Well, that'll be 1/2 times that stuff, 9x squared plus 1, now to the minus 1/2, times the derivative of the inside stuff, 9x squared, which will be 18x. And let's just do a little bit of housekeeping on this problem, and then we'll see what we have. Okay, so that stuff to the minus 1/2 will go to the top, become 9x squared plus 1 to the 1/2, 9x squared plus 1 to the 1/2, just write that down. And in the bottom there, we're going to have a 2, which will cancel with the 18. So that'll all be over 9x. We got a little bit of a problem. If I do L'Hopital's rule again, the bottom, that's just going to be 9. The top is just going to be all this stuff again. Which would leave a 9x up top, which would cancel with that 9. And then you're going to have all this stuff move back to the bottom again. So in other words, if I do L'Hopital's rule again, I'm back here. Oh, yuck. Ouch. So L'Hopital's rule actually doesn't work on this type of problem. Okay. So with that in mind, we have to try another approach. And so the other approach actually requires me to think of it more as the square root. So I'm just going to rewrite this as a square root. Limit as x goes to infinity of the square root of 9x squared plus 1 all over 9x. Okay, so as I look at this, the top, or the bottom, is degree 1. The top has an x squared, but it's inside a square root. So that's kind of like degree 1 as well. So what I need to do is get something to cancel out. So what I'm going to do is I want to be able to, so what I do is I come back here now and I say I wanted to divide, since this is basically x and x, degree 1 and degree 1, I want to divide by something out of the top and bottom, just to kind of rewrite how things look. So what I'm going to do is I'm going to multiply the top and the bottom by 1 over square root of 9x squared. Leveraging the idea that I'm going to positive infinity. So therefore, when I'm going to positive infinity, x is positive. So the square root of x squared will actually just be x. So when I do it in the bottom here, square root of 9x squared will just be 3x. And that 3x will cancel with the x there. So in the bottom, when I do this multiplication, I'm going to have limit as x goes to infinity of just 3 in the bottom. Because this is going to be 3x, 3 and the 9 cancel to be 3, the x's cancel, and we just have an x in the bottom. In the top, I wrote that as a square root so I can get it inside there. So that square root will actually go inside now. And when it goes inside, you're going to have 9x squared divided by 9x squared, which will be 1, plus 1 divided by 9x squared. Okay, now I've transformed this so it's no longer an infinity over infinity limit. Now it's a limit where I can just let x go to infinity. And when I do, that stuff there is just going to become a big fat 0. And I'm going to have the square root of 1 plus 0 over 3. And so this all is just equal to 1/3. So therefore this limit, this sequence here, converges to 1/3. Okay, so this is an interesting one. Anytime you run into with this square root of a square over an x, you will not be able to do it with L'Hopital's. It's just going to keep repeating that cycle over and over and over again. So you have to use this idea, right? Multiply by 1 over the square root of that stuff. That lets you distribute into that square root, and when x is positive, as it is here, that lets you convert back to x, which can simplify with that. So this is going to converge here to 1/3.